I want to give some talk that's a little more narrowly focused than the previous ones, but it does connect sort of the considerations of astrophysics with those of general relativity, black holes, and gravitational waves. So I want to describe some recent work on the relativistic evolution of orbits around a spinning Kerr black hole. The astrophysical context for this is a massive central black hole in a galaxy surrounded by a cluster of stars. Those stars are close enough that they predominantly orbit on Keplerian orbits around the black hole, but they perturb each other. And so in a diagram where you plot the semi-major axis or the energy of a given star versus its eccentricity, and this is circular at this end and very eccentric at that end, so this is 1 minus E, stars typically evolve at roughly constant A, but do a random walk in eccentricity. Every once in a while, a star can pass this barrier, which is a barrier induced by the relativistic advance of the pericenter, and then a star can get sufficiently close to the black hole that suddenly gravitational waves take over and the star plunges toward the black hole, circularizing and then going to very small semi-major axis and enters the black hole. So on this same plot of 1 minus eccentricity, or angular momentum, versus semi-major axis, this regime is the regime of people who do stellar dynamics, stellar clusters. This regime way down here in the corner is the regime of interest to LISA, where the final orbits of the object around the supermassive black hole emits gravitational waves that LISA could detect. And this Schwarzschild barrier is kind of this region where stars have to cross it. This is a region where the time scale for precession of the pericenter of a given orbit is short compared to this relaxation time scale, and so those relaxation effects are suppressed. So that barrier impedes stars getting close to the black hole. But when a star can cross that, it might start here in a very eccentric orbit, maybe 0.999, a modest semi-major axis, and then proceeds down toward the black hole. And what I want to do is to use general relativity to try to link this regime where a star has been injected into some final orbit. One thinks that maybe you can ignore further stellar perturbations and then follow that pure GR orbit quantitatively down to the point where the star plunges and ask, what does that final plunge look like, and how might that tell us something about the gravitational waves that are emitted? So everyone who knows me knows that I'm going to do this using post-Newtonian theory, even though this is motion around a black hole, but still the distances are large enough that PN theory might be a good approximation. So, and I'll just outline the method and go straight to the results. So first, one imagines the equations of motion around a black hole break down into two sectors. There's the kind of conservative sector where you can treat the particle as a test body. We're imagining a 50 solar mass black hole orbiting a 1 million or 10 million solar mass black hole. So this object can be assumed to be a test body. And so you just look at geodesic motion. But around Kerr, we want to transform first Kerr into harmonic coordinates. These are not the usual coordinates of standard textbooks, but harmonic coordinates are the ones that are used for post-Newtonian theory, for gravitational wave theory. So it's a natural coordinate system to use if you want to link to other areas of gravity physics. But that's a well-known transformation. We will use the geodesic equation in this conservative part of the motion. And you can then expand Kerr through third post-Newtonian order. Well, in fact, you can expand to infinite order, but we'll work to third post-Newtonian order. It will include all the spin orbit effects, the frame dragging, the effects of the quadrupole moment of the black hole, the spin squared effects, and so on. So with this order, you get all the relativistic effects, including those depending on the spin. Then there's the radiation reaction sector. This is where now you turn on the mass of the small black hole, because you need a finite mass to have radiation damping. And so these are governed by this small parameter, the dimensionless reduced mass parameter, which we will assume is small compared to unity. And we will work here just to first order in this small parameter. In this sector, of course, that parameter just produces small corrections, which we will ignore. Here we have equations of motion at 2.5 post-Newtonian order. That's the standard quadrupole formula for radiation damping, but corrections to that at 3.5 and 4.5 post-Newtonian order are known, so we can write those down. And some years ago, we worked out the spin orbit terms in the radiation reaction equations that now therefore take into account the spin of the black hole. So all those terms can be put together. And then we use standard orbital perturbation theory to look at the secular evolution of the orbital elements of a given orbit, the semilattice rectum, eccentricity, inclination, and so on. But here, since we're going to high orders in a post-Newtonian approximation, you can no longer do what you often do in textbooks, namely let the orbital elements be constant on the right-hand side, integrate over one orbit to get the secular evolution. You actually have to iterate these Lagrange planetary equations over and over and over again, since you're going to high orders in a post-Newtonian approximation. So you have to do a second order, third order, fourth order expansion in the Lagrange planetary equations to get all the terms consistently. And the results look like this. Just to illustrate a few of them. For example, in terms of this dimensionless parameter, the semilattice rectum scaled by the black hole mass. In terms of orbital phase, the dimensionless spin parameter of the black hole, I is the inclination of the orbit. Then the semilattice rectum and the eccentricity evolve in a certain way. These are the leading quadrupole formula terms. These are the so-called Peters-Matthews terms that you see in old papers and in standard textbooks. And then there's the 3.5 corrections, 4.5 post-Newtonian corrections. And then there's the spin-orbit corrections that change sign depending on whether the orbit is prograde or retrograde. So that will change the evolution of the orbit depending on the inclination of the orbit. The mass doesn't appear in any of these expressions, so as other speakers have noted, in a correct representation, the mass of the black hole is irrelevant. The only place the mass re-enters the problem is if you want to learn about the actual time scales, like the orbital period, so that the mass appears there. Otherwise, these are all dimensionless scale-free equations that you can analyze and study. And so here's the next thing you have to do, of course, is terminate the orbit. This particle then will orbit the black hole, it will shrink, the semi-major axis will decrease, and it will reach a point where the angular momentum of the particle's orbit is smaller than the critical angular momentum, such that that particle will no longer have an inner turning point in its orbit. In other words, it will get closer to the black hole and will keep going closer and ultimately cross the horizon. So that's a critical angular momentum for capture by the black hole. And in many calculations, you assume that that angular momentum is 4 in units of the black hole mass. That's the critical angular momentum for a Schwarzschild black hole. But for a spinning black hole, frame dragging actually changes that. So for prograde orbits, and this is these different colored curves depend on the inclination of the incoming orbit. So prograde orbits actually are captured at much lower angular momentum than retrograde orbits. Well, prograde orbits get much closer to the event horizon of the black hole before being captured. Retrograde orbits get captured from much further away from the black hole. And this will have a strong impact on the final orbits. And in fact, you can write down a very good fit to these numerical solutions. There's an analytic formula that you can derive that gives an excellent fit for almost the entire range of the Kerr parameter, chi or A over m. So combining those evolutions with this capture condition, then one can evolve orbits on this same phase space diagram of semi-major axis versus eccentricity, or 1 minus eccentricity. Here are two orbits injected at various initial values of the semilattice rectum in units of the black hole mass, and with eccentricities of about 0.999. And then they evolve, and then in the late stage, evolve toward the final capture. And I'll blow up that last part so you can see the differences between a retrograde orbit, say here, that reaches this point and is captured, and notice that the eccentricity is quite substantial. The prograde orbit gets much further close to the black hole and is finally captured. It's much more circularized than the retrograde orbit. So you can see the small differences that really just build up as the system gets more and more relativistic. You can ask, what's the eccentricity of the final orbit just before the plunge? And so here, plotted against the initial semilattice rectum from 20, say, to 100, final eccentricity. Starting from larger distances, orbits circularize more. That's what general relativity tells us. So the final eccentricities are lower, say 0.04, and down. But injections from, say, closer, if you reach the final unperturbed orbit closer in, the final eccentricities can be larger. And for retrograde orbits, the final eccentricities can be quite large indeed. Again, the orbits are captured from much further away from the black hole, so they don't circularize as much. So this may help to inform calculations of those final orbits, knowing quantitatively what kinds of eccentricities you might expect in those late stages. You can ask, what is the energy flux in that final orbit? We have formulas for the energy of the third post-Newtonian order. We have the rate of change of the orbital elements at comparable orders. So to that high post-Newtonian order, you can calculate the energy flux. And if I normalize that energy flux to what you would get for a pure Schwarzschild black hole, which is independent of inclination, so I just normalize that to this, and ask what is the energy flux as a function of inclination, so normalized, as a function of the black hole spin. And you see that for spins of 0.2, 4, 6, and 8, retrograde orbits emit much less energy than prograde orbits in that final orbit, and in some cases by factors of 100 to 1,000 times smaller than for prograde. So if you're making estimates, for example, of the detectability of Emery radiation for LISA, you should be aware that just using a Schwarzschild calculation may not give the entire picture, because if orbits are injected with random inclinations, then the average energy flux may be rather smaller because of this strong dependence. And again, it's primarily due to the fact that retrograde orbits are captured from further away than prograde orbits, and so they emit less energy in the final orbit. You can also estimate the gravitational wave frequency as a function of inclination, again normalized to the Schwarzschild case, but for prograde versus retrograde orbits. Finally, you can calculate the time to plunge from an initial injection, say from initial simulatus rectum of 20, 50, or 100. You see that the different inclinations take different amounts of time to merge. And it turns out that there's an analytic formula that fits this time to merger over a very large range, orders of magnitude range in times. And here's the formula that might be useful for people who want to make a quantitative link between the evolution of a central cluster around a black hole and use that time scale to predict analytically when the star will plunge and therefore be taken out of the simulation. So this turns out to be a very accurate representation of these numerical results. And I could describe the hypergeometric function that leads to that specific dependence on the eccentricity, but that would be too boring. So I've tried to provide a link, a quantitative link, between the nature of stars in a central cluster that are coming toward the black hole because of stellar perturbations and the final state just before they plunge, and giving you some idea of what the time scales and the properties of those orbits might be. Thank you. Jerry.
An interesting consequence of the retrograde orbits having captured from further is that there's a larger cross-section for capture. So if a black hole grows by accreting gas, then you expect it to have a high spin. But if it grows by accreting stars, then you expect it to have a very low spin, because it tends to accrete a larger number of objects going in the opposite direction from its spin, which will reduce its spin, whatever the spin is.
Right. And also conversely, stars with negative angular momentum are captured from the cluster, and so in some sense the cluster on average gets more angular momentum. It's losing angular momentum in a preferential direction.
But all of those angular momenta are very, very small compared to the cluster angular momentum, but large compared to the black hole angular momentum, so that they affect the black hole a lot, but not the cluster very much.
Yeah.
But it would tend to give you central black holes with very tiny spin.
Right, depending on the total rate of capture in the cluster.
All of your results you gave as a function of the initial peak, right? Injection.
It's the angular momentum.
Angular momentum. Now, that is presumably determined by the properties of the surrounding cluster. What do we expect for a typical galaxy? Who must have calculated this?
Well, so in those simulations that I showed, I mean, that particular one was for a black hole mass of 1 million solar masses and a certain number of stars in the central cluster.
It must be more than numbers, right? You need to know something about the order distribution
Right.
and orbital properties.
I'm sorry. Yeah, so I mean, I couldn't give a quantitative answer, but it's the kind of thing that people, try to simulate with these n-body simulations.
Any other questions?
Expand on Jeremiah's question. You think there's any connection between the radio loud black holes that we see with jets that presumably have non-zero spin and the way they accrete their matter? I mean, is there any connection with spin in that regard? I mean, the black hole in the center of our galaxy, for example, doesn't seem to be spinning. We don't see a jet. M87, ostensibly spinning, well-studied jet. Is one eating stars in a certain way and one is not?
I don't know. I mean, that's a question for a more astrophysical question than I can answer, but maybe someone can help out.
I guess I could take a crack at answering that. These black holes grow both by eating stars and by eating gas. Also by merging with other supermassive black holes. And each of these has its own effect on the spin of the black hole. So in any given system, you have to ask, the last doubling of the mass, was it primarily by eating stars, like Cliff was calculating, in which case Jerry's point would be absolutely valid? Was it mostly by eating gas in an organized disk, in which case its angular momentum would have grown quite a lot? Or was it through a merger? I don't know what that does, but I presume it's something in between. So in other words, Cliff is absolutely right. This is an astrophysics question. It's dirty. It's not this beautiful, clean, post-Newtonian expansion.
Which is why I do that.
I know. Okay. Thank you, Cliff.
Okay, so can you hear me if I speak close to the microphone like this? So, most of my talk has been given away by the excellent introductions we had this morning. For example, unless you were sleeping, you have seen this plot of the first detection by LIGO several times. And you also heard from Daniel that we did a series of papers in collaboration with Chris Belczynski and Michael Dominic on predicting the rates for these things. And I think we were pretty lucky because in one of these papers, we came up with a standard rate with huge uncertainties, of course, that was pretty much close to the 1 per day in advanced LIGO that Matt Evans was quoting this morning. If you rescale that by the fact that we were considering advanced LIGO design sensitivity and we didn't take into account for the duty cycle, you will get from that number to an estimate of about 4 events, which is pretty close to the 3 or 2.9 that Daniel was talking about. What we really didn't expect was this. We really didn't expect that the first event to be seen would be from a binary of 2 black holes that were way more massive than the ones that were detected in low-mass X-ray binaries, and that the final black hole would be that massive. That certainly we did not expect. And when I got the paper from PRL, was one of the few to see it, besides the 1,000 people in the LIGO collaboration. Before publication, my jaw literally dropped because I never would have expected such a clean in-spiral merger ring-down signal for the very first detection. Now, one thing that people started thinking about immediately was, well, now that we've been surprised and we have seen a signal with such a large signal-to-noise ratio, can we test gravity for real? And what we're testing with these systems are the Einstein equations. And I will not go through the abused quote by John Wheeler, but effectively, if you want to modify the Einstein equations, you have 2 options. You can modify the gravity sector, the G mu nu on the left-hand side, or you can modify the matter sector. And my talk will be organized around this idea. I will try to answer the question, what can you test if you modify the gravity sector, and what can you test if you modify the matter sector using gravitational wave observations similar to the boundary black hole that we have seen. So what I will argue is that if you modify GR, you can modify it in several ways. You have very tight constraints, of course, for doing so. But these will very often lead to the same metric as in general relativity. There are several modified theories of gravity, as Dimitrios, for example, pointed out some years ago, that admit the Kerr solution as one of the many solutions. But all of these theories, once you introduce additional degrees of freedom or whatever, they have dynamics that are very different from the dynamics of the Kerr metric. And this is something that we can test. We can also test, I will argue very briefly, more exotic ideas, like the presence of quantum corrections at the horizon and stuff like that. The other option is that we modify the left-hand side of the Einstein equations. Sorry, the right-hand side. I'm looking at this from the opposite direction. So if you modify the right-hand side of the Einstein equations, what happens is that one of the most popular modifications these days is to look for dark matter degrees of freedom because we have cosmological reasons for doing so. And so what I will argue is that if you introduce ultralight dark matter candidates, these can produce very distinctive signatures in gravitational waves that are potentially observable. And I have a little surprise at the end of this talk. So let me explain the very basic physics behind all of this. Essentially what happens is that if you take a Kerr black hole solution and you perturb it, you can separate out the angular variables like you do when you solve the hydrogen atom in your elementary quantum mechanics class. And you come up with a radial wave equation that is essentially a one-dimensional scattering problem with a potential barrier. Now, if you are in general relativity, this potential barrier is pretty boring. It goes to 0 at the horizon of the black hole. It has a maximum that is very close to the light ring at 3m, or, you know, for a Kerr black hole somewhere else, but it doesn't matter. And it goes to 0 at infinity. Now, you can imagine scattering a wave on this potential. So you send a wave of amplitude A. Part of this wave is transmitted through the barrier and goes inside the black hole. Part of the wave is reflected and goes away to infinity. You can ask yourself, are there proper modes of oscillation that would be there even when the amplitude of the incoming wave is equal to 0? Those are called the quasi-normal modes. They are the proper modes of oscillation of the black hole in the absence of an external perturbation, okay? And you can compute the spectrum of these modes. It turns out that it's a spectrum of complex modes. These can be computed once and for all, and they depend only on the mass and the spin of the black hole. So that's the boring situation. At the end of my talk, I will address the situation of a Kerr black hole in the presence of a very light, massive scalar field. What changes in that case is that the potential doesn't go to 0 at infinity anymore. It goes to some finite value that is basically mu squared, where mu is the mass of the scalar field, in the right units, of course. So what happens is that in this case, you create a potential well. And as you know from quantum mechanics, in a potential well, you can have bound states. In fact, these states are not bound, they are quasi-bound, and they can decay. So what can happen now is that if your black hole is rotating, you may have one of these quasi-bound states that is in the superradiant regime. You throw in a wave. This wave is partially transmitted through the barrier. Partially it's reflected with an amplitude larger than the original amplitude because you're in the superradiant regime. And so when the wave goes to infinity, it's reflected again by the barrier that you have due to the mass of the field, and you create a superradiant instability. This is called a black hole bomb. It was studied in 1972 for the first time by Press and Tukowski. So this creates essentially a monochromatic signal at a frequency that is determined by the mass of the field. If the mass of your field is in an astrophysically interesting range, then you can have a stimulated emission of gravitational radiation that is potentially detectable by LIGO. Keep it in mind for later. So the first half of my talk has been scooped by several speakers this morning. But the main point that I want to make is that if you have a black hole of mass m and spin a, it's not enough to detect the signal, as we have done with LIGO. If you want to test the no-hair theorem, you need to detect more than one mode. So here I show you a plot of the kind of signal-to-noise ratio that you need to tell that there is a second mode in the signal and carry out one of these tests as a function of the mass ratio of the boundary. I'm ignoring spins in this plot because it's simpler. So the curve that you have to look at is the intersection of the dashed blue curve and the solid blue curve. And you see that for a mass ratio close to unity, as in GW150914, the typical signal-to-noise ratio you will need to detect this second mode is around 80. And if you go to the LIGO paper that was shown several times this morning, the SNR in the ring down for that paper is about 7. So you need an extra order of magnitude. And the question is, if you take all of the different designs that Matt Evans was talking about this morning, when are you going to get to the point where you see 2 modes in your signal so you can clearly test the no-hair hypothesis? So what I did, as Matt Evans said, was I took all of the different noise curves that they published over the years, and I also took the different LISA proposal noise curves that were put forward before the most recent L3 study team report. Before the recent proposal to ESA. And this is the plot that Matt showed this morning, except he didn't show this part. And so what you see here are all the different noise curves for Earth-based detectors. O1 is up here. Advanced LIGO design sensitivity is the solid black line. And then you have Voyager, which is the best detector you can build in current facilities, and that's the solid red line. Green is ET, and blue is Cosmic Explorer, this thing for which you need to take into account the curvature of the Earth and dig a 40-kilometer tunnel. So that's kind of the best thing that you could do on Earth, given a nearly infinite amount of money. And then what you see here are different LISA designs. The one that is in the last proposal that was sent to ESA is very close to what we call N2A2 here. So it's very close to the original classic LISA design. Now, a couple of things I want to point out. If you take the ring-down frequency for a Kerr black hole, for a typical spin such as in GW150914, it's about 170 hertz for a black hole of 10 to the 2 solar masses. So it's in the bucket of the Earth-based detectors. If you want to go to the bucket of LISA, you need to go up in mass by about 10 to the 4, okay, 4 orders of magnitude. Now, if you compute the signal-to-noise ratio, you see that LISA seems to lose in terms of strain sensitivity with respect to LIGO, and even worse with respect to the other Earth-based detectors. Where it wins is in the strength of the signal. Because if you compute the signal-to-noise ratio, you see that it depends on 1 over the distance, some factors of order unity, 1 over square root of s, which is what I'm plotting here, and the mass to the power 3 over 2. So if you go down in frequency by 4 orders of magnitude and up in mass by 4, you go up in SNR by 6 orders of magnitude. So what you would expect is that LISA will do roughly as well, if not better, than the best detectors on Earth. That's the punchline from this plot. But now, as Shep was asking this morning, if you want to make this more quantitative, you need to plug in some astrophysics. So what we did was we took several models from Chris Belczynski's Star Trek team. M1 is what he calls the standard model, where the black holes that you form from collapse are at most 100 solar masses. M10 are models where you have pair instabilities that prevent the formation of black holes more massive than about 50 solar masses. And M3 is the most pessimistic model you can cook up, where he allows all black holes to have kicks as large as the kicks that neutron stars would receive. So most of these binaries are disrupted, and the event rate goes down. Here we have 3 models that I got from Enrico Barause and the collaborators, where the black holes are formed, as in previous work that we did with Marta many years ago, in 2 ways, either from light seeds or from heavy seeds. And in the case of heavy seeds, it turns out that it's also important to take into account the final parsec problem, whether there's a delay between galaxy mergers and black hole mergers or not. And the results were shown this morning already, so I'm not going to discuss them very much anymore. But the bottom line is that you will always detect ring downs in the future. We have already detected them in O1, and it will only get better as you go to better and better detectors. But if you want to test the Kerr hypothesis using Earth-based detectors, you need something like Voyager. With LISA, every time you have a detection, you can also test the no-hair theorem. And also, the main difference is that you see the number of events is the most uncertain, because we don't know very much about black hole formation. So they can go from a few to hundreds in the models that we got from Enrico. The other main difference is that, instead of testing the no-hair theorem in the local universe as you would do with advanced LIGO or even Voyager. With LISA, you can go to very high redshifts if those black holes are out there and merge at all. So you have these very high sensitivity probes at very large Z. Now, the other thing that I want to point out is that this is a pessimistic scenario where you want to detect the second mode in a single event. You can be more clever than that. And there's a paper out there by Young and others where they say that if you take several detections from LIGO and you stack these events, then you can test the no-hair theorem by cleverly combining the phases of the subdominant modes in several low SNR events. But I will not explain this. Let me skip also this part that is more speculative. Maybe we can talk about it in the question and answer session, which is about gravitational echoes and quantum gravity effects at the black hole horizon. I will skip all of that. But what I want to point out is the little surprise at the end. So I told you that you can have these superradiant instabilities, and the superradiant instabilities can produce several interesting effects. If you want them to be astrophysically relevant, you need mu-m of order unity, because that's where these instabilities are stronger. If you plug in the numbers, it turns out that mu-m for a black hole of order 1 solar mass is of order 10 to the 10. So you need either a very light boson to have mu-m of order unity, or a very heavy black hole, okay? And here you see that whenever those superradiant instabilities happen, the expected outcome from perturbation theory, and now also from numerical simulations that were carried out by Easton Pretorius, is that the black hole will spin down. So if axions or light particles of the given mass that is indicated here exist, then you would not have black holes that spin faster than what is shown in these instability windows, okay? And the black points are estimates of black hole spins from electromagnetic observations. The red points are the LIGO estimates, okay? Now, you can use this idea to rule out certain ranges of the light boson masses, but what we've been asking recently, and we have a paper that should come out hopefully within a few weeks, is are these axionic signals detectable by LISA and LIGO? So let me explain this plot very briefly, and I only have this and an extra slide, and then I'm done. So what I'm showing here are different axion masses, the LISA noise curve, the LIGO noise curve. This is the SIGO that was mentioned this morning, if we could build it hypothetically. And what you see here are, we fix the black hole spin to be 0.9. It's not even that extremal. We take sources, individual sources, that are located at redshift from 0.01 to 3, and then we let mu-m grow in the superradiant, in the regime from 0 to where the superradiant instability is possible. And as you can see, the signal increases, and for some values of the axion mass or light boson mass, these signals become detectable. In fact, for some masses, the stochastic background from all the signals in the models that we have would be detectable itself and be a source of noise for the detectability of the resolvable signal. So if you want to assess, this was a surprise, this we did not expect, that if you take all the individual black holes out there, then you get a detectable stochastic background of signals from axionic particles if they are in the right mass range. And then we did this plot, where this is the surprise. What we found is that if you take even the O1 data, there is a certain mass range. These are frequency integrated sensitivity curves for those of you that are familiar with the detection of stochastic backgrounds. There is a certain window in the mass of light particles where they are already ruled out by LIGO data. So we should probably go back and do the analysis more carefully than what we did in this very simple plot, because we might be already digging into detection of dark matter with LIGO, and we haven't realized it yet. So these are my conclusions, and if you want to talk about more exotic things, we can do it during the question and answer session. Thanks.
Thank you. Time for questions?
Yes.
So about this superradiance phenomena you're talking about, and this mu m equals 1, which is a condition 2, get efficient, I guess, superradiance. I guess what you really mean is the Compton wavelengths of the
That's exactly.
particle equal to the Schwarzschild radius. So I guess my question is, so you're really doing quantum mechanics around the horizon. So I guess my question is, to what extent is this kind of phenomenology it's valid, given that you're doing quantum mechanics near the black hole? So
I am not really.
it's
All
really
of these,
quite general phenomena. You
Yeah,
don't have to
these are
worry
purely
about quantum
classical.
gravity kind of, fuzzy black hole kind of issues. Or it's a very robust kind of.
this is very, there is no, we're not even using semi-classical gravity at all. This is a purely classical calculation where all you do is you take a scalar field or a Procap field in the background of a Kerr black hole, and you just look at classical perturbations. So most of the estimates that I've shown here are based on perturbation theory, but there are calculations now by East and Pretorius where they looked at Procap fields using full numerical relativity. You just evolve the Einstein equations with a test field.
So H bar enters only in the scalar field part.
It only enters in the mass units. This is a classical calculation. Yeah, Priya maybe? Or, okay.
So for these instabilities to grow, you're converting basically the spin energy into the modes that get amplified. And as you mentioned, the calculations were perturbative.
Yes.
But the key question is how does this instability saturate and which fraction of the rotational energy goes into those?
Yes.
How confident are you that you can extract? I assume that your limits are based on an assumption on how much of first of all, how much spin there is to those black holes, and second, which fraction of it goes into the scalar?
Yes, that's an excellent question, and I'm glad that you're asking me that question now, because until maybe 2 weeks ago, I would have had to wave my hands and tell you that we expect that the most energy you can transfer is given basically by the Christodoulou formula and blah, blah, blah. But now I can do more than blah, 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 because there are actual simulations that were done by Will East and France, where they did a clever thing. We knew already, because we did calculations in the slow rotation approximation, that vector fields and gravitational fields have a growth rate of the instability that is much faster. And the big problem has been so far that the time scale that is associated with black holes is the dynamical time scale m, and the growth rate of this instability is much longer. So if you want to watch the growth of a scalar field, you have to run your simulations for unrealistically long times. Because the vector instability is so much faster, they said, well, let's try to evolve that. And they used some extra tricks to reduce the dimensionality of the problem, and they could do it. And they found an answer that is perfectly consistent with my hand-waving explanation that the most energy you can transfer is given by the Christodoulou formula, and so the perturbative predictions that we're using in the estimates match the numerical simulations by East and Pretorius, which is great.
So, Emanuele, what kind of ultralight particles are you? These are not ultralight. The ultralight axions that are sort of fashionable in the moment, right? They're much lower mass than what you're looking at. So what particles do you have in mind when you're talking about? Because the ultralight are minus 22 eV to
Yes.
minus 30-ish, right? Sort of
So
that
those are
range.
the ones that people are considering within cosmology. Those are not testable, as you can see here. And basically, what we are just taking an agnostic point of view where we say, let's suppose that there's a spectrum, what people call the string axivers, of particles that are formed somehow. Andy probably has much better ideas of high energy scenarios in which things like this can be formed. But we're just saying, let's suppose that particles of any given mass that is potentially detectable given what gravitational wave detectors are sensitive to are out there. Can we see them? If we can, bingo, we know they're there, and then we will have new, hosts in the standard model that we can play with. And if they're not there, then we can just rule them out, which is also very interesting. Oh yeah, that's what I would expect, but looks like we already can, which is kind of amazing.
Okay. Let's thank Emanuele.
Thank you. So we listened to a number of wonderful talks about testing general relativity and the Kerr hypothesis using gravitational wave observations. And in the next 15 minutes, I would like to take a complementary approach to argue how one can do similar tests in a very complementary way using electromagnetic waves, and in particular, the black hole in the center of our galaxy. And to put that in context, I usually like to start by showing this plot, which quantifies the strength of gravitational fields that we expect to find in astrophysics. These are the places where we can test general relativity or any theory of gravity for that matter. And in the x-axis here, I have just plotted the gravitational potential divided by c squared, because this is a nice dimensionless quantity that tells you how relativistic you are. And of course, everything to the right of this red line is behind the horizon, so nothing to the right of the red line is accessible to any observations. But if you think about modifications to gravity, it is extremely unlikely that those modifications, classical modifications, will depend on the value of the potential. It is a lot more likely that it will depend on other quantities of the gravitational field that are a lot more fundamental and geometric, things like the curvature, for example, gm over r cubed. So when you look at this two-dimensional parameter space, you can place astrophysical systems from cosmology, clusters of galaxies, the solar system and stars, all the way to white dwarfs, neutron stars, stellar mass black holes, and supermassive black holes. And the point to take out of this parameter space is that a priori we do not know if any modifications of gravity exist where on that parameter space they are. We don't know whether we're not talking about Planck scales, but we're not sure whether we're talking about horizon scale modifications or perhaps some sort of screening mechanism that crosses part of the parameter space to be GR correct and part of the parameter space to require a modification. Until recently, most of the tests have happened with, around the solar system or with pulsars. But what has been really remarkable over the last decade or so, and of course for the future, is we started building as a community a plethora of experiments that are going to probe different parts of the parameter space using different types of observations. And if you remember down here, it was the cosmological probes, and there's a number of experiments that are practically dark energy or barrier acoustic oscillation or structure formation experiments. But for the purposes of this talk, we need to focus on this part, which is the various black holes of different masses. And you can take the sensitivity curves of various experiments and convert them on regions of the parameter space that you can actually probe the gravitational fields. So LIGO is up here at the strongest curvatures and near horizon scales. LISA or ELISA is down there, and the Event Horizon Telescope is down here, and the pulsar timing arrays are over there. The point to take out of this diagram is that even though we're talking about black holes, no matter which experiment we're using, we're talking about black holes of very different scales, and having this 4 or 5 different types of experiments spanning the entire range of black holes of known masses will actually allow us to map the gravitational fields in many, many different regimes. Now, this plot is not enough to talk about the complementarity of electromagnetic wave observations versus gravitational wave observations. One is to think a little bit about what kind of tests we're doing. And the fundamental difference is that when it comes to electromagnetic wave observations, we're really probing and testing the quasi-stationary regime of the theory. We're not really testing the fundamental theory, we're testing metrics. On the other hand, gravitational wave observations, whether they're in the relatively weak or in the strong regime, test primarily the dynamics of the theory. And on the one hand, the dynamics are very, very important. As Emanuele pointed out, there are many modifications to gravity that leave the black hole solution unchanged, but change the dynamics. On the other hand, doing tests in electromagnetic waves is much simpler because we don't have to worry about the fundamental theory. We only have to perturb the metrics and figure out what their perturbation parameters are. Perhaps more importantly, those events are catastrophic. They come and they go. That's why we heard about the ring-down modes that don't last for that long. The electromagnetic wave tests are events that are reproducible, and we keep on going back and refining our tests and refining our observations. So having said all of that, I'm going to focus, as I said, on the black hole in the center of the Milky Way, and this is a radio image of the center of the Milky Way. If you haven't seen it, the black hole is hidden behind that bright emission over there. It's a black hole of a very well-known mass, a few million times the mass of the sun. It's at the center of the Milky Way. And it is the one that subtends the largest opening angle in the sky because it combines the biggest mass and the closest distance between the two of them.
And the goal, as many people talked about, is to find ways, find different observables to measure higher moments other than the mass of the space-time, things like the spin of the black hole and the quadrupole moment. And if this is really described by the Kerr metric, then the no-hair theorem tells you that the spin and the quadrupole have to be on that line. In other words, the quadrupole has to be equal to minus spin squared. And if you make an observation that sets the combination of spin and the quadrupole far off, then you suddenly have a way to, or a very strong argument that what the underlying metric is not described by the Kerr metric. The minute you say testing or probing gravitational fields with astrophysics, the first thing that comes to mind is orbits. This is, astronomy for thousands of years. And there have been a number of papers over the last 15, 20 years by Norbert Wex and Sergei Kupening and by Cliff here 10 years ago, when they looked about the relativistic effects in the orbits of stars and pulsars around the central black hole. And the two main effects are, in one case, you will have, when you have an orbit on the plane of the equatorial plane of a spinning black hole, the orbit will precess, just like Mercury does. And that primarily measures the mass of the black hole. This is the dominant effect, and the higher order moments are subdominant. But if the orbit is inclined with respect to the spin of the black hole, the orbit will precess, and that precession will measure the black hole spin due to frame dragging and the quadrupole moment because of quadrupole precession. Now, just with a single star or a single pulsar doing the relativistic effects on the orbits, you can measure a combination of the two. If you have more than one, because of the different radial dependence of the phenomena, in principle, you can break the degeneracy. The problem with that, these kinds of events, is that the orbits around the central mass of the Milky Way are very eccentric. And therefore, when the star or the pulsar is far away from the periapsis, then there are a lot of classical effects that affect the orientation and the precession of the orbits, the interaction with the stellar cluster. And again, Cliff and David Merritt have written a wonderful paper about that, that make it possible, perhaps, only if you find the proper star or the proper pulsar very, very close to the horizon, much closer to the black hole, such that the effects of the surrounding cluster are not relevant. However, when it comes to pulsars, you don't have to wait for the orbits to precess, because pulsars are wonderful clocks, and by observing the pulsars, you're actually doing a ranging experiment. And by ranging, I don't mean the geometric distance, I mean the flight time distance of the photons. And what that means is that as the pulsar goes near its periapsis, both the velocity evolution of the pulsar that determines the Doppler effect and the Shapiro delay that determines effectively an integral of the line of path throughout the space-time depends very strongly on the quadrupole. And this is a simulation that we did recently with Norbert Wex and Michael Kramer, showing the residuals in the pulsar time of arrival measurements with realistic error bars that you would expect if you have a single pulsar within, give or take, 15 days from its periapsis. This is not waiting for the orbits to precess. This is really mapping the space-time around the periapsis. And the residuals depend entirely on the quadrupole moment, and the residuals are enormous. This is about half a millisecond. And if you have seen any pulsar timing residuals, you know that people are talking about hundreds of nanoseconds. This is a really, really, really strong measurement. And even if you take one or a few of those periapsis passages and you have the black hole spin and the black hole quadrupole before, then you can constrain very well the spin and the quadrupole of the black hole. And of course, the more periapsis you go, you don't have to worry about the rest of the orbits. The limits become tighter and tighter. This is beautiful, but it has one minor problem, that we do not know of any pulsar near the galactic center. And there's a very good reason for that. There's a lot of scattering between us and the galactic center. We hope we'll find one, but this is something that we cannot do today. There is something else, though, that we can do today, or we did a week ago. No, the observations happened about a month ago, and I'm not going to talk at all about the project itself, because there is an entire session tomorrow that is going to talk all about the details, other than to say that the Event Horizon Telescope is a collection of pretty much every millimeter telescope around the globe. You can see all of them. The last, or this one and Greenland were not part of the last observing run, but as of last month, the Event Horizon Telescope took data for two major black holes in the universe, one in the center of the Milky Way and one in the center of M87. And the primary goal of the Event Horizon Telescope is to take pictures with a horizon scale resolution of the inner accretion flows around them. There's an incredible amount of science that the HT will do, which, as I said, I'm not going to talk about in this talk. And I just want to focus on the pure gravitational effect, which is measure the properties of the shadows that the black holes are going to cast on the surrounding emission. The idea of a black hole shadow is something that goes back to Bardeen and Luminet, and this is from the actual paper by Luminet that you see. He imagines the black hole being back illuminated by a flashlight, like a laser pointer, and calculates the size and the properties of its shadow. We don't have to do that anymore because we have very elaborate GRMHD simulations that allow us to measure, to predict, I should say, what the observations of the image are going to look like. This is what you would see if you were to take the observation at 3 centimeters because the accretion flow is optically thick. But as you take down the wavelength, increase the frequency, the accretion flow becomes optically thin. And if you put it just right at a millimeter where the Event Horizon Telescope works, you actually see the shadow being back illuminated and appearing in the image. Now, our goal in the gravitational aspect of the HT is to measure the properties of the shadow and say something about the gravitational field. And I want to be very clear here that the accretion flow is there only to illuminate the shadow. We don't care for the test about any of the properties of the accretion flow. It just provides the photons on which the shadow is cast. So this is a test that is as clean as it gets in the electromagnetic spectrum. And originally, we thought that what we're going to do by measuring the properties of the shadow is measure the spin of the black hole, because as you spin the black hole, the photon orbit becomes closer to the horizon, and the space-time becomes oblate. But when we started calculating the outlines of shadows for black holes of different spins, we found something unexpected, which is that when you spin up the black hole, the shadow remains circular of the same size and moves towards the direction of the black hole. And that turns out to be an unexpected coincidence. The effect of the quadruple, which is to make the shadow oblate, is completely canceled out by the effect of frame dragging that pushes one side of the shadow against the other. And you end up with something that effectively doesn't care about the spin of the black hole or the orientation. This is horrible news if you want to measure the spin of the black hole with this method. There might be other ways to do it with the Event Horizon Telescope that you're going to hear about tomorrow. But it is a great null hypothesis test for general relativity. Because we effectively have no free parameter, there's nothing that we can do to the metric, as long as it is a Kerr metric, and change the opening size of the opening angle and the size and the shape of the shadow. And what will happen if we start playing with the metric and add modifications that change the quadruple, different than what the Kerr hypothesis says? So this is, in this particular case, we fix the spin, and we deviate the quadruple by this amount from the Kerr value. And what you see is that the minute the no-hair theorem is not satisfied, when Q is not equal to minus a squared, then the black hole shadow becomes asymmetric and oblate. So just by doing that very simple measurement that does not care about the accretion flow, only cares about the outline of the shadow, will allow us to tell something about how different the spin from the quadruple moment of the Newton of the black hole is. And as I said, just as we were doing before, this is the kind of accuracy that we expect to have with the Event Horizon Telescope. If you assume a particular black hole spin and assume that it's Kerr, this particular test will never tell you what the spin is. You really do not know where you are here, but it will tell you, surprisingly, how far away you are from Kerr. And this is something really, really remarkable because, as I said, there's no free parameters, there's nothing to play with. It is either there or it is not. And it is not enough. What if it turns out that the data does not put it on Kerr but puts it up here? Will you then believe me that we measured the deviation from the Kerr metric? Well, maybe you will say, let's wait for a few years to find a pulsar and maybe a star, and then we will have 3 different ways of measuring the exact same spins and quadruples of the exact same source with completely independent and orthogonal systematics. And if all 3 of them fall on top of the Kerr prediction, then we call it a success. If all 3 of them fall away from the Kerr prediction, then we really start believing and wondering what is the underlying metric of that black hole. And I would like to stop here. Thank you.
Sorry, you must mean to first order in something, right? It's not an exact statement that the shadow is a circle. I mean, Bardeen showed already in 73, there's the flat edge.
Correct. So this is really the asymmetry of the shadow, the formula down there, which is the relative size in the vertical, like along the spin and perpendicular to the spin. So at the quadruple order, the two effects cancel out and you're a perfect circle. The minute that the spin goes higher, becomes very close to 1, really beyond 0.95 and so on, then you start becoming sensitive to the octuple of the space-time and higher order moments and becomes more oblate.
Yeah.
At the extreme limit, it becomes very non-circular, which is exactly the plot that exists in Bardeen. But this is something that really is at the limit of very, very, very high spins.
Yes. So you're using, the light is coming from some kind of, in your model, is coming from some kind of accretion flow?
Correct.
And so, I mean, in that picture of Luminet, that's a backlit black hole, right?
Correct.
So an accretion flow will have stuff coming from, so apparently that's unimportant for some reason.
So you can see that there's some things that are sticking in front of the black hole at different wavelengths. Maybe if I go back as it starts popping out. So here you see everything, of course, in front and behind. And then when the accretion flow becomes more or less transparent, here it's kind of blocked, and then you go to higher and higher frequencies, it becomes less and less relevant. It all depends on the relative transparency of the plasma. And the reason that you see the one side a lot more brighter is because of the very strong Doppler shifts. So these are really things that are behind the black hole that gravitational lends towards you, and the very large velocities make them to appear very bright. The things in front of you are pointing perpendicular to you, and therefore the transverse Doppler shift is not significant to make them too bright, either for emission or absorption.
So why isn't the intensity of the ring as a function of angle a good measure of the spin? It seems to show up in your simulation.
Why is it, or is it not?
Why isn't it?
Oh, it would be great, but then you would have to know how the ring is illuminated, and that depends entirely on the astrophysics of the black hole. So yes, if you believe your model of accretion, and actually I think Avery might show some of that, you can measure the spin extremely accurately. However, if I make the accretion flow thin or thick, or if I change the relative transparency, that changes, unfortunately, a lot the angular distribution of emission from the ring.
Just curious, couldn't you use G2 or even the subsequent passages of G2 to do, to constrain? This is
You mean
blob,
the orbits
blob.
of the...
Yeah. Or does it just not sample close enough?
G2 does not go anywhere near where you want. You want to be inside the S2 orbit, which is, you want to go to a few hundred Schwarzschild radii to start measuring even the spin.
But there's future propagated, right, orbits of G2.
And G2 might evolve, right? G2, I mean, it depends on whether it's a star or not. Yeah.
G2 has an orbit that is quite, probing the same region of space as S2. But the other thing about getting 100 Schwarzschild radii is that, of course, stars would be torn apart by the tidal gravitational field of the black hole. So you need a very compact star to be able to survive there. And, obviously, a remnant like a neutron star or white dwarfs might do so, but they're not as visible.
Correct. Good to say, Avi. This is a paper we wrote together last time I was at Harvard. There is indeed an optimal sweet spot of semi-major axis where what the blue lines show here are the various relativistic effects that you want to measure, and what the red and the green and the gray areas are the places where other effects are actually dominate the signal. So you want to be, I mean, this is the semi-major axis, and the eccentricity is meant to be 0.5, 0.8, 0.9. You really want to be in the few hundred Schwarzschild radii that you can have a star before it gets tidally disrupted. That's the pink line, and you can barely see the effects of the quadruple. So it's a tight spot for that. Hopefully it will happen.
Just a very brief comment on that. Of course, our friends at UCLA and in Germany are busy trying to add substantially to the list of stars. It's one of the things the next generation telescopes will do, right? So and those are nicer than G2. We don't know what it is. It's the great event that wasn't, et cetera.
This is a simulation of what you expect to see. The rightmost from UCLA using a 30-meter telescope with next generation adaptive optics, an extrapolation of what we think the stellar cluster is going to be. The leftmost one is the stars that we know right now. Correct. any tracer is great.
So Dimitrios, going back to the beginning of your talk, where you showed that two-parameter space, I think you kind of said in passing that it's unlikely that gravity would be modified as a function of this epsilon parameter. I would have said the opposite. I would have said, GR has got some particular simple scaling, and maybe there are higher powers of GM over R C squared that come into the theory, or some F of R and all of these things, that there must be a whole family of non-GR models which are just fiddling with this horizontal axis, the dimensionless number, rather than some dimensionful number which you've got vertical axis. So what is your thinking for saying that this is unlikely?
The qualitative answer to that is that the potential is not something that you can write easily in a relativistic invariant way. So any modification of gravity that you can think with minor exceptions actually does not depend on the potential. Even if you think about it in terms of GR, this particular scaling, the GM over RC squared, is not specific to the field equations. It's actually the equivalence principle. It's the Lorentz symmetry that gives you that scale, which is effectively to say that what happens in the horizon is a observer-specific event. Now, it might be that any quantum modification and the kinds of things that people like Andy and Andrea and other people are talking about, the horizon is relevant for a different reason. But any classical modification, if you want to write it in a way that is coordinate invariant, observer invariant, it is extremely unlikely to do it in this way. Things that people are looking in cosmology, like all these screening mechanisms, F of R gravity as you talk, this is a curvature scale. The Weinstein mechanism, it's primarily a radius scale, a length scale, as opposed to anything else. And there's different ways of doing, you can do a kinetic modification, that's an acceleration scale that reminds you of Mond. It is extremely unlikely to make a modification that's potential dependent. Classical modification.
Very good. Okay. Thank you, Dimitrios.
Thanks. Yeah, so I'm Reed, and that was a long title. Hopefully it will be an interesting enough talk to justify it. So we've heard a lot about how to test general relativity, and particularly with black holes, things like quasi-normal mode frequencies. I'm going to talk about how to maybe do this with matter effects being present, and really this talk is a cautionary tale of some of the troubles that might happen with that. So the first thing I think we're all familiar with is compact binary systems. I'm focusing primarily on things that have at least one neutron star. So we assume that the neutron stars, have small spins. The black holes may have larger spins. There are a lot of complicated, very interesting dynamics there. But what I'm primarily interested in is what happens to this squishy bit of matter that's orbiting around at relativistic speeds, and how exactly do we test general relativity when there are these other interesting physical effects going on. So the tool that I'm going to describe to you is something called TIGER, so the test infrastructure for general relativity. And this is one of the pipelines that the LIGO and Virgo collaborations have put together to test general relativity. And specifically what it's trying to do is Bayesian model selection, and it's computing what's called an odds ratio. So this is a very natural thing to compute, and I'm going to run through sort of the logic and how it's computed so that everyone's on the same page. The odds ratio is basically just a ratio of the posterior probabilities of two different models, which I've called A and B here, conditioned on the data. So it's the ratio of how likely I think model A is compared to model B based on what I saw, which is exactly what you want, to do science based on. So how do we compute that number? That's a good number to go for. The first thing is use Bayes' theorem to invert the expression. So you can write the likelihoods times the prior. And then to get those numbers, what you actually need to do is marginalize over all your model parameters. So if you haven't guessed, I'm primarily a data analyst. So this is the type of stuff that I do all the time. But let's break down this number a little more carefully. The thing on the far right is called the prior odds, right? This is just what you think before you see anything, right? So if I really believe model A or GR is correct, I might weight that very strongly when I compute this number. If you're more agnostic, you might give that unity, and therefore you're just looking at the data. The other thing, the long expression, is the ratio of the evidences. Now, what exactly is this evidence? Usually it's called Z, and basically it's a marginalized probability distribution. So you take all your model parameters, theta, right? And this could be the masses of your system, the spins, if you have any matter effects, all those things, and you marginalize over those. You integrate those out, And the probability of getting the data given each parameter integrated over these things is the evidence. It's a measure of how well your model fits your data. Right? So this is what you compute for each model you have, and then you can compute these ratios, and that tells you which model you prefer. Right? So this is what Tiger does, and it's sort of a well-evolved and studied and characterized pipeline that the collaboration uses. This is what it's actually computing, right, is this odds ratio. So it's with two models, the point particle model, which for us is basically a post-Newtonian expansion for point particles with spins and stuff like that. It's pretty clean. This is what you would expect from a nice, clean black hole system or a vacuum solution. And it's comparing that to what I call the not point particle model. So this is some sort of deviation from general relativity. And the way it does this is it takes the post-Newtonian expansion for the phase, right, which is going to look something like this, and it introduces modifications to the terms. So GR says these psi's, each psi j, should be some function of mass, spin, all that stuff. But if that's wrong, if there's some modification, you can tweak that by throwing in these other parameters. And the nice thing about Tiger is it's not specific to just a fixed change. It can use one deviation, it can use two, it can use n, and it checks all these different combinations for you, does the proper combinatorics, and really does compute just the point particle versus anything besides the point particle odds ratio. So this is, honest to God, what you want to do sort of a null test of GR. So this is the number that it's trying to compute, and I'm going to come back to this at the end of the talk. But the reason that the actual use of the post-Newtonian expansion is important here is that you rely on that being the correct model for GR, what physics is actually going to give you. And if you have squishy neutron stars there, linear tides and merger things can do messy things to your signals, particularly at high frequency. So, excuse me. Part of the solution to this is, or at least that people have proposed, is to just truncate where you look for things. So this plot is a little busy. On the x-axis is frequency. On the right is the A-LIGO PSD, the sensitivity curve, with the red numbers giving you the scale there. And on the left is the fraction of the SNR that you accumulate as a function of frequency. So it's really 1 minus that fraction. So at 0 frequencies, I haven't accumulated anything yet. That's why it's at near 1. And at high frequencies, I've picked up all my SNR that I'm ever going to get. So it goes down to 0. And the proposal here, based on a nice review study that was done by some people in the collaboration, is that linear tides and this merger stuff really only become important above something like 450 hertz, which means if you look below 400 hertz, you're going to be pretty insensitive to that stuff. And if you look at the scaling here, at 400 hertz, which is roughly here, you're going to be losing 1%, maybe 2%, of your total SNR. So that's non-trivial. You can't just completely write that off, but it is a relatively small effect, so you're not going to completely destroy your ability to make measurements. So the proposal here to get rid of all these matter effects is just don't look at that part of the waveform, right? And rely on where you think the post-Newtonian expansion is good, which is at low frequencies. The problem with that, and here's the cautionary tale, is if nonlinear tides that are raised within the neutron stars are large and significant, those affect exactly this part of the signal and mess up exactly where you think you have a good model. So before I give you the punchline of exactly how much this can mess us up, let's describe what these nonlinear tides are a little bit more. The basic idea is you have some sort of perturbing body that's raising a tidal bulge. You can parameterize that with some epsilon parameter, this small number here. And the canonical statement that everyone says is, well, epsilon is small, therefore linear theory is appropriate. Well, that's not quite true. What measures the smallness of the perturbation is really this epsilon, which goes like the amplitude of the modes that you raise, times the nonlinear couplings between those modes. So it turns out in neutron stars and degenerate stars in general, these couplings, 3-mode couplings between different modes of oscillation in the star can be quite large. And therefore the product of kappa times epsilon, or the amplitude, may still be small, but it's not going to be vanishingly small. And therefore these sorts of effects can become important. The PG instability is particularly interesting for binary inspirals because it's secular. So once it turns on, once the amplitude gets big enough that it turns on, which we think is going to be about gravitational wave frequencies of 50 hertz, it just grows throughout the inspiral. So you accumulate a bunch of phase. So the way that works is we think that you're just going to be dumping energy into the neutron star from the orbit. And that's going to scale, we think, with G-mode braking. So G-modes, the gravity restoring force, restores these modes. Basically, they grow, and at some point their displacements become comparable to their wavelength. That's when they overturn, or what we call breaking. They scatter modes into, or energy into smaller length scales. So what drives the energy dissipation rate then is the rate at which they grow, gamma, the number of modes that participate, and the energy at which each one saturates or breaks. So you get this very natural estimate of what the total energy dissipation is, and we model that in terms of an overall amplitude parameter that has some uncertainty in it. There's a frequency dependence, so as the orbits get closer together, you expect the tides to be stronger, therefore this thing might grow. And as I mentioned already, there's this turn-on thing. So we model that with a Heaviside function. We think we're pretty insensitive to the exact form of this, but this is what our phenomenological model has. So with this, right, you then have this extra sink of energy, and in your time domain waveform, before it turns on, there are actually two curves here, but they lie right on top of each other. So one is the point particle model, or your base GR model, and the other one includes this nonlinear phase error. After the thing turns on, so with this particular plot, it turns on at 50 hertz. So this is at 43, this is at 56. You can see a phase error starts to accumulate, right? So what's happening here is that your waveforms get out of phase and you start to lose some of the match. It doesn't match as well. What this looks like in the frequency domain is something like this. So as a function of frequency, this is the phase error that you accumulate, and bigger amplitudes, you get bigger phase errors. This is exactly what you expect. The way we actually define this in the frequency domain is a slightly modified post-Newtonian expansion, and you get very simple things. We then do some tricks to try to model exactly how these nonlinear parameters depend on the masses. All this to say, we have some phenomenological model for what these things will do. We put it in, and we want to see how it actually affects our ability to recover signals. So this is what that's doing. As a function of the nonlinear amplitude parameter here, this is how strong your tides are. This is the odds ratio, which I explained at the beginning of the talk, between the GR model, the point particle model, and just Gaussian noise. So when the tides are small, you get most of your signal back. You recover it, and it's pretty flat here. And then when the tides start to get bigger, you start to lose some of your evidence for that signal. What that's telling you is that your model is not matching the data that well anymore, right? So this is one of the main conclusions of our paper, is that when these tides are big and strong, you can actually just not recover signals because your data doesn't match the model that you think it should. Well, let's pretend that we have this phenomenological model. Then you can start saying, when is the nonlinear tides model a better match than just the GR point particle model? Turns out it's basically the same thing, 10 to the minus 8. It starts to turn on. And instead of all the curves going down, they start going up, right? So, okay, great. I've now described the model to you that includes these nonlinear tides. We think that they're real. There's a large uncertainty here. You can see I have 3 orders of magnitude. That's basically because that's the uncertainty in how loud these tides are. But for some values, this number, this log odds ratio, can be quite big. So, the ratio here of the nonlinear model versus the point particle model is e to the 50, which is big, right? So that's very confident then that the nonlinear tides are real. So if we zoom in here, like I said, this point right here, this little blue one, the log odds ratio is 53. So this is when I have the perfect model to recover with, right? And the interesting thing is, if I throw this through Tiger and give Tiger the general relativity model and say, hey, does this match? It comes back with a log of not PP versus PP of 45, which is pretty darn close to 53. So even though Tiger knows nothing about the exact form of this deviation or anything like that, it's very robustly able to detect that there's something there, right? But remember, this is not a modification of the GR. This is a matter effect that we neglected. Right? So this is the cautionary part of the cautionary tale. If we're going to do sort of, precision measurements and tests of general relativity using neutron stars where there's matter, we really have to get the general relativity model perfect, right? Or at least as close as possible. Because if there's any sort of physics that we have neglected, our pipelines are good enough to pick that up. And they'll say, hey, there's something wrong with your model. And before we run off and say Einstein was wrong and we have a fancy new theory, we need to make sure that neutron stars behave exactly as we expect. So with that, if I've piqued any of your interest, I highly recommend reading any of these papers, particularly this one. But with that, I'll take your questions.
Of consistency and convergence of the priors, to fix stable posteriors. But there are well-known theorems that show that you don't get consistency and convergence in the case where the parameter space you're dealing with is nonlinear or non-Euclidean or infinite dimensional but still countable, and all of those conditions hold here. So what justifies you in using a Bayesian model? And I mean, if we don't have confidence that these arbitrarily selected priors are going to converge to something reasonable, why should we trust this?
So my first counterpoint would be that the priors are not arbitrary. They're motivated astrophysically. For instance, in the local universe.
So you're assuming that you're assuming you know the answer, basically, in order to justify convergence and consistency?
No. For instance, in the local universe, I expect sources to be distributed uniformly in co-moving volume, right? That's a completely reasonable thing I think we can say. Now, if I look at the posterior probabilities, right, that come out of our analysis pipelines for things like the actual detections, the distance posteriors look nothing like their uniform and co-moving volume. So basically what the prior is flat enough and sort of broad enough that the likelihood, right, let me go back up to the evidence slide. This integral, right, is what we care about. And it turns out that this function is very sharply peaked, that it's pretty insensitive to what you actually pick here. So I agree that, if you have some sort of extremely broad parameter space, you could run into problems.
I find that hard to believe because these theorems show that dense subsets of these, in situations of this kind, dense subsets of the parameter give you non-stable, non-consistent, non-convergent behavior.
Perhaps we should talk about this more offline because I'm not familiar with this, but this is my understanding that it does work, at least in our situation.
One advantage that such systems offer relative to a binary black hole merger is that there could be an electromagnetic counterpart, and you haven't touched much on that. So the question is, if we were to see fluctuations in the light curve, or is there any hope that the combination of time domain in the electromagnetic sector and in the gravitational wave sector could assist each other in terms of figuring out better what's going on?
Yeah, I think there definitely is. I think part of the issue with that is a lot of what people have targeted in the electromagnetic is after the things have smashed together and broken to bits, right? So that sort of makes it more difficult to figure out exactly what they were doing before they smashed together. But there are, of course, some models that would predict radiation before the actual merger and things like that. If you are lucky enough to see those things, I think that you can definitely combine that information in a usable way. In fact, it can also tell you things about the nonlinear tides, because the energy that comes out of the orbit has to go somewhere. So it might be heating up the core of the neutron star, which then would affect things like the kilonova or such signals like that.
Well, it's more to do with short gamma ray burst than the kilonova, which is a much later event, right?
Sure.
Any other questions?
I can just to follow up on that, and I think this is part of the interesting point here is, where this turns on. And that's related to equation of state and various other things. And, in some ways that might be where you first get emission. And so for, fluffier versions, you get emission earlier before the merger, something that in principle could be measured.
So Avi has an announcement, I think, but before that, let's thank Reed and all the speakers this morning.